Got a few different slide decks for this, all from University of Virginia, so they've got a decent rendering course over there. So, the first thing is to talk about the rendering engine and what it does. A lot of this in Unreal, we're not going to get into the nitty-gritty depths of it, but it's important that you understand what exactly the rendering engine does, why it's important, why we have a scene graph, that kind of thing. So the job of the rendering engine is obviously to render the scene from the camera and potentially other viewpoints. Other viewpoints becomes interesting because obviously we may need to have picture-in-picture elements or split screen or observer cams, that kind of thing. Also, quite often we need to take a sort of a shadow map or figure out a calculation of a shader, and quite often that will have to come from another viewpoint that's rendered over the back buffer. This is called rendering multiple times from the same viewpoint. That happens with blending, multiple shaders, deferred shaders. Basically, we do another pass over the rendering engine and achieve the look that we want to achieve. In certain settings, we might need color, for example. We might want to do low-res textures, do various LODs. And as I said, we might need a different render target or a viewport. So we have to access the scene first, and we do so by the scene graph. The scene graph is basically a complex representation of the every object in the scene. It's usually a spatial representation, and it can be represented through things like trees, and essentially it's everything connected in its place in the scene relative to each other. The scene graph allows us to interact with other components such as the physics engine, the animation engine, the AI engine for things like sight lines. Essentially what it is it's a hierarchy representing objects and relationships. If you think about, for example, the gun and the turret of the tank, that's a hierarchical representation of where that gun is. The hand on the forearm, or the upper arm, on the trunk, mouse on the cheese on the table. It's a directed acyclic graph, a DAG, with arcs representing relationships. And basically the nodes represent arcs. So for example, let me show you a quick example of that. You might have something that looks similar to the following. So we'd have like, oh, what the heck is that? I don't want that. If this is the overall node, that's the scene root, for example. We might then have, for example, one room, another room. Here, I'm just gonna So, for example, if we had a situation where these were all in the scene graph, so the idea would be that you'd have the scene root up here, and then you'd have sort of a living room maybe. The TV is in the living room, a bathroom, the sink is in the bathroom. That's sort of what a scene graph is meant to represent, is nodes, and then inside of those nodes, the scene root obviously is basically the house, and that includes the bathroom and the living room. Inside of those is each of those is separate objects. Those objects and groups of objects. The actual geometry may only exist at the leaves. The rest are going to be groupings. LOD selectors, animation effectors, various transforms. Typically we traverse this in a depth-first manner. We start at the top, so like the scene root, looking for example, what's visible in the scene. So on to the next sort of topic here. Classically, what we do here is we traverse the graph looking for things. We can optimize the traversal by doing per frame computations, bounding boxes, matrices. We can flatten the hierarchy. The reason we're doing this traversal is things like view frustum culling, cells and portals rather. Here's a few simple traversals. So here's one way that this might look in code. So, for example, we've got a point, which is an array. Got a triangle, which is an array of 3. And then this actually does the vertex rendering for each of those triangles. Now, as far as efficient rendering, which is a very important topic, there's 5 main steps to efficient rendering. The first would be to reduce vertices, reduce the overhead for each vertice, and then recognize the existence of the vertex cache, and then display the list, and finally learn about any hardware optimizations that can be made. So all of this comes down to visibility, which is what this next section is about. Because essentially we don't want to render redundant geometry. We don't want to render geometry that can't be seen. We take care of this through view frustum culling and object occlusion. Efficiency is very important here because we do not want to render items that are occluded by other items or off screen. That will drastically slow down our renderer. So we want to quickly eliminate large portions of the scene. We call this conservative estimate of what we should be rendering the potentially visible set, also known as the PVS. This was sort of the old approach with clumping. The modern approach works by cells and portals. So we basically walk through architectural models, divide these into cells, alcoves, corridors, And then we have transparent portals connecting the cells. So for example, here is where we are, and each of those would be kind of like what I gave you in the earlier in the scene graph, where we have the living room and the bathroom, for example. And the cells end up forming the basic unit of our PVS. We create an adjacency graph of these cells and see where other cells are, which ones are visible, and that allows us to chunk off huge sections. So for example, in this map it would be, we'd have A through G. A, B, and C are off on the left there. A is potentially visible from C. As you can see, there's a portal there. C is potentially visible from H. D is potentially visible from H. G is potentially visible from H. F is potentially visible from E. So we end up forming a adjacency matrix out of all of that, and that's what this type of data structure is down here. So let's say we're in E. Well, we look at this graph and we can see that potentially visible from E is F and G and D. Therefore, we can clump out A, B, C, and H. So we do not need to draw those. Now, it's a level of detail thing. If we wanted to, we could still draw them. But if we want to be efficient, we would only go one level deep, and therefore we draw D, F, and G. I don't know what that was all about. So that's basically it. The rest of this view independent cells, I was going to essentially skip. You can take a look at the portals algorithm, which is a depth first adjacency graph traversal. Treat portals as special polygons. If it's visible, render the adjacent cell. That's essentially what I was just describing. So that's sort of the end of this video, and make sure again to get in your homework 3s and get your game pitches going. I will be posting this video online, but for now I'll be ending the GoToMeeting unless you got any questions. Yeah, so yeah, I should mention that the source of this is from Lubke and Georges, 1995. That was the PF portal algorithm. So if you want more details on that, you can read up on here, including some pseudocode for it. So, alright, I'll be posting this. Thanks, guys.